Welcome to part 2 of this video series. So this time we are going to look on power and thermals of the electronics. We are still outside of the Streacom chassis. So we want to, before we move into the conduction cool chassis, check where we are in terms of thermals and power. We will now be stress testing the electronics and keep track of the power consumption and look at the thermals of all the electronic components. For this purpose, we are using the following set of tools. There is M Prime. If you are a Windows user, you might know the tool Prime 95. M Prime is the same thing, just compiled for Linux. We'll be using this basically to generate stress on the CPU and on the memory when we are running it in blend mode, or we will be using it to stress exclusively the CPU when we are running it in small FFT mode. The small FFT mode is basically doing calculations on data which is small enough such that that data will fit entirely into the cache. So like this, no relevant access outside of the CPU is really happening, and like this we are only stressing the CPU. Another tool that I'm using to generate stress is a tool called Stress NG. So this is a suite actually which has a variety of options to create stress on several components. In that scenario here, we are using that only for stressing the DDR memory. As a third tool, there is iPerf. iPerf is a utility to measure Ethernet throughput. This is used here to actually measure the bandwidth we can achieve on the 10G Ethernet, and then also see how the thermals behave on the heatsink of the 10G Ethernet device. Further, for testing the NVMe and the SATA SSDs, we have just a DD command just to take data from the drive or write it to the drive, and running multiple DD instances in parallel on all of the drives. Like this we can generate a lot of load. To capture the sensor readings, we can use LM sensors. So this is there to read out all the sensors on the motherboard, on the CPU, and so on. Yet another thing that we are going to use to look at the thermals, in particular on the thermals of the heatsinks, is a FLIR1 camera. So this is an infrared camera which is shown here on the right. This one can be plugged onto an iPhone, or there is also an Android version of it. And what it does basically is it allows to capture infrared images, and like this it allows to visualize the heat. And finally, what we are going to use is the IPMI that I introduced already in the first part briefly, to look at sensor readings on the board as well. In the first part of this video series, I was always talking about the impact of having no airflow. You might have wondered, why am I so concerned about this? If we are having a scenario where we use airflow for cooling, we have coolers on top of the devices. Those coolers will have fins, and then there is forced airflow blowing through the fins, which is carrying away the heat. If we have no more airflow, the coolers will just warm up the air around them, and then what happens is what is called natural convection, meaning warm air is ascending by itself, and that movement is what is responsible to carry away the heat. However, that movement is much less intensive compared to the forced airflow that we are having when we are using a fan. Now let's try and demonstrate this effect. Here is a test setup that can be used to show this. What I'm looking at is actually the X570 chipset. Well, I noted during early tests that actually it is getting quite hot, which triggered me to look a bit deeper on what is going on. We can see that I put some paper around the X570 chipset. This is actually the user manuals of the Noctua NHP1. I use this just to shield any airflow that might be present in the room, just to not disturb the measurement. I have a fan prepared on the side. This one is already connected and blowing air in a direction where it doesn't interfere with the measurement as well. So we will use this in the course of the measurement to place it in front of the X570 chipset and then observe what is going to happen. So on the front we can see an iPhone. That one has the FLIR camera mounted, and that FLIR camera is taking a video of the heat distribution on the heatsink of the X570 chipset. We have the video feed of the FLIR camera appearing here on the right. Here we can see that it's doing 3 measurements in total. So the first one, the crosshair that is shown, is actually the temperature measured at the location where the camera is pointed at. The second part, the crosshair with the red marking, is the hottest spot in the visibility of the infrared camera, and the crosshair with the blue spot is the lowest temperature in the visibility of the infrared camera. Obviously the 10 to 12 degrees that it measures there cannot be correct. We are sitting in a room where we have an environment temperature of like 23.5 degrees, so it cannot be that there on the system we have temperatures colder than that. So this clearly shows limitations that we have when measuring temperatures with infrared. It is a larger subject, but when measuring with infrared, the temperatures measured do not only depend on the temperature of the object under observation, but also it depends on the surface of that object. So therefore we'll take the absolute temperature values that are observed with the FLIR camera with a grain of salt. Still, it is relevant to look at difference of temperatures observed with the FLIR camera. We'll do this towards the end of this analysis. And in addition, we are looking over IPMI to use that sensor to also observe the die temperature of the X570 chipset. Like this, we have 2 independent measurements, and if with both measurements we are coming to the same result, we have established credibility that the results are actually valid. The system here has been already running for a while, so I just let it heat up. It is completely idle, so I'm not instructing the CPU to do any transactions over SATA or anything. We are just sitting in idle. And here we observe that the hottest spot on the heatsink here is already at 85, 86, 87 degrees. I could not find the datasheet of the X570 chipset that is available publicly. So I cannot really say how close we are to the maximum operating temperature of the device. But what I can say is that by experience, those chips operate up to 95, 100, 105 degrees, but at latest at 105 degrees this is normally too much for the device. When reading over IPMI, we observe we have 88 degrees. When reading the temperatures of the heatsink over the FLIR camera, we see that we are somewhere between 85 and 87 degrees. So the order of magnitude is correct. However, we cannot make assumptions on the temperature difference between the die and the heatsink because of the uncertainties with the measurement on the FLIR camera. So we got 88 degrees in idle in open air on the X570. The system is going to be a NAS system, meaning it will be standing around in idle quite a bit. So here we are measuring 88 degrees in idle in a completely open setup. So we have an environment temperature of 23.5 degrees. Now if we imagine that we put that setup inside the Streacom chassis, here we will have of course restrictions on the airflow. It is not completely closed, there is some air evaporating out of it, but it is natural to assume that the air inside will warm up. So maybe it will warm up by 10 degrees, maybe it will warm up by 15 degrees or even 20 degrees. I cannot really say, I can only assume. But if we assume that the air is warming up by 15 degrees, then the 88 degrees we are suddenly looking at like 103 degrees. And having 103 degrees in idle on the X570 chipset does not make me comfortable. So already at this point in time, we can say when operating that configuration in the Streacom chassis, we need to find a custom solution for cooling the X570 chipset. So let's see what happens when we put the fan. So first I remove the paper that is used to shield any airflow, and then the fan is placed in front of it. So I was moving the fan a bit just to be sure that the infrared camera has visibility of the entire heatsink, to make sure that we are really capturing the hotspot. The fan was just put right now, and you look at the red temperature, we are already at 78 degrees. and it keeps dropping. So we already won 10 degrees now within a couple of seconds. And now we are going to let this run for another few minutes, and then we see, how the temperature is going to be in the end. So while this is cooling down, I will also say that when filming that video, I was doing that same measurement multiple times. So the measurement is completely reproducible. Now what happened here was that actually the heatsink of the X570 was cooled down so much that the hotspot shifted away from the heatsink to something else. We can see on the lower corner, this is the heatsink of the 10 gig Ethernet device actually. So what I did is I just placed something in front of that such that the infrared camera does not see that heatsink, so we can continue to observe the temperature of the heatsink of the X570 chipset. And here we see we are now at 55 degrees already. So we won 30 degrees already. Let's still continue to observe and then we see where we will end up. We are just about to hit 50 degrees, so we are winning 35 degrees already on the heatsink. This is enormous. So it's been just a few minutes and we are approaching the 45 degree boundary. So we are approaching a total temperature difference of 40 degrees that we have measured with the infrared camera. Let's look on how the value is on the IPMI. So here we see also a rapid temperature drop to 49 degrees. In the beginning we were at 88 degrees. So here we are observing a temperature difference of 39 degrees. So we have a difference measurement on IPMI with 39, with the infrared camera of 40 degrees. So that's basically within measurement precision the same value. So we have two independent measurements which confirm that we have a dramatic impact when we have no airflow cooling. As a conclusion, cooling without airflow is much harder than the other way around. I'm definitely not saying that companies who are making airflow-based coolers are not facing challenges. For sure, this is also quite a subject. However, when having no airflow, it is still yet a different thing. So in summary, I explained already before that I'm assuming that the temperature inside the Streacom chassis will be hotter than the room temperature here, so the air will warm up over time. So like this, the 88 degrees will get higher. Assuming we have 10 degrees or 15 degrees higher air, we are somewhere between 98 and 103 degrees. So like this, the conclusion is quite clearly we need to define a custom heatsink for the X570 chipset. The other observation is we are observing a temperature difference of 40 degrees. If we are comparing a situation where we have enforced airflow with a fan compared to having only natural convection without the fan. As a next component, let's look at the 10G Ethernet. So for this device, this is the X550 chip from Intel. A datasheet is publicly available. This clearly specifies that the maximum die temperature is 103 degrees that the device can handle. I followed the same strategy like for the X570 chipset to on the one hand observe with the FLIR camera the temperature of the heatsink, while at the same time comparing the temperature measured over IPMI. We can see that the highest temperature captured over IPMI is 76 degrees, while the highest temperature I could capture on the heatsink with the FLIR was 72.4 degrees. This experiment was also done at a room temperature of 23.5 degrees. Again, the readings are consistent, so the order of magnitude of temperatures observed is fine. However, unlike the X570, we are in a different range. On the die temperature, we are 12 degrees lower compared to the X570 chipset. On the X570 chipset, we measured a maximum of 88 degrees, while here the maximum is 76 degrees. Again, this measurement was done in idle. The Ethernet links were up, but I was not running any benchmark and it already went up in these temperature ranges. I've also tried measuring temperatures under load, so using iPerf to generate traffic on the device. However, I could not observe a significant temperature difference. As on the 10G Ethernet, we are 12 degrees lower compared to the X570 chipset. Even if we assume that the air temperature inside the chassis will be higher, we are still, if we assume it's 10 degrees higher, at 86 degrees. If we assume it's 15 degrees higher, at 91 degrees. If we assume it's even 20 degrees higher, at 96 degrees. So in any case, we are below the maximum operating temperature that is specified in the datasheet. Nonetheless, I was not comfortable operating a device continuously above 90 degrees. So for this reason, I decided to be cautious and still design a custom heatsink for the 10G Ethernet device. As a next step, let's look at the memory. So here we have the DDR4. For this measurement, stress NG was used to generate load on the memory. So what we saw here, this in the worst case, we were measuring 65.6 degrees Celsius. I looked up the datasheet from Micron on the chips which are used there, and they state that the maximum operating temperature of those is 95 degrees. So we have a 30-degree margin. So again, the air inside the chassis might be hotter, but we have a 30 degrees margin under full stress, so likely the DDR is going to be fine already. Nonetheless, so I found online just some copper shims that can be put on the SO DIMMs. They will just distribute the heat a little on top of the devices. So I think with the DDR, with this will be just more than fine. As a final part of the thermal analysis, let's look at the CPU. So the cooler that is used here is Noctua NH-D14. This is obviously complete overkill for that CPU. But for reference measurement, it was important that we have a cooling solution which will definitely not be the bottleneck. So here I was running the M' in small FFT mode, so only inside the CPU, not any other components outside, so we are running completely in cache. And I was actually doing two measurements, so one with the carbon thermal pad and another one with the ICE5 thermal paste that was delivered with the chassis actually. What we see there is the temperatures reported from the AMD CPU, so the die temperature and the CCD2 temperature, which is mostly the same. We can see that with the carbon pad, we are like maxing out at 64 degrees C, while at the ICE5 under load, like the minimal temperature is 64 degrees C. So in a direct comparison, the carbon pads are a little better than the ICE5 thermal paste. What we see here is a cross-check on the frequencies of the CPU cores on the two test scenarios. So the first row here was taken using the carbon pads, and the second row here was taken using the ICE5 thermal paste. We can see that in both cases the frequencies stayed stable. This is important because the CPU could also stay within temperature boundaries if it clocks down its own frequencies. So we need to look at both things. We need to see that the temperatures are fine, and we need to see that the frequencies are on an even level in order to be able to say whether the thermal solution is good or not. So here we can see that all the lines are straight, so the frequencies were okay, so that means the thermal results were actually comparable that we had before. Here's a cross-check of the ICE5 thermal paste. So here the question is just, was it applied properly? We need to be able to say that the entire area was evenly covered with thermal paste. If, let's say, we take it off and there would be a spot somewhere where there is no thermal paste, this would mean that the paste was not applied properly, and I guess the measurements are wrong. But as we can see here, it was evenly distributed, so the cross-check here is also fine. Next to that, I was also doing analysis on other potential hotspots in the system, like the VRMs, power supply, the NVMe, or the SATA SSDs. However, in none of them I could identify any thermal risks. So I decided to just go with the standard cooling solution that is already present on those devices. As a next step, let's look at the system power consumption. So the idea is to find out, will the power supply that came with the chassis be good enough to power the system that we want to build? So for this I did an analysis searching datasheets on the web to find out how much power the individual components consume. So we'll do an analysis on the worst case power consumption and then a measurement in reality to find out how the worst case power consumption is in reality actually. The AMD Ryzen 5600X, this is information that is easy to find, has a TDP of 65 watts. But while TDP 65 watts does not mean that the CPU is really consuming the 65 watts constantly. So we have dynamic clocking mechanisms. So what I found out by searching the web is that the worst case power consumption of the CPU is at around 90 watts. So we'll do a measurement later to see how this looks like in more details. The X570 chipset, I was not lucky to find a freely available datasheet for this. I found some people who did analysis on the power consumption of that chipset, and the number that was coming out there is somewhere between 10 and 15 watts. So I was not able to really find a hard number, just a span. So I will just say, okay, for the X570 chipset, we are going to calculate with up to 15 watts. The Ethernet, there the datasheet is freely available on the internet. There's a table in the datasheet which says depending on which speeds the channels are used, the power consumption is given. So I can say that if we are running one channel at 10 gigabit Ethernet, the other one at 100 megabit, that the chip will consume in the worst case like 10 watts. For the SATA SSD drive, it is also quite easy to find the information online. Also there is a datasheet available from Samsung which states that the worst case power consumption is 2.2 watts for the device in the worst case. As we have 4 devices and the 4 devices will be operating in parallel due to RAID, so we can say that for the SATA SSD drives our worst case power consumption will be 9 watts. For the Samsung NVMe drives, it's a similar logic, so also there the data is available, it's also used in RAID, and here the worst case power consumption of an individual drive is 4.6 watts, so we are coming up to a total of 23 watts for those in worst case. For the NVMe carrier, there was no information available. I found, when I opened it up, I saw that there is some electronics on the carrier. It is not clear for what purpose they are used, so I do not really have a hard number on how much power the carrier is going to consume. I assume it will be almost nothing, but not zero, so just put in 1 watt, just for the sake of having it there. For the DDR memory, it is actually not so easy to find out what the power consumption is exactly. The memory power consumption depends highly on how it is used, so like this, even Micron says they are not giving just a simple number to say this is the power consumption of our devices. Instead what they do is they just give an indication saying do a rough estimation of 3 watts per 8 gigabytes in the system. So if we are running with 32 gigabytes, the memory will be 12 watt maximum. If we are going with 64 gigabytes, then it will be 24 watts for the worst case consumption. In the end I decided to go with 64 gigabytes, so the 24 watts will be the number for our system. We have also the mainboard to consider, so there is not much components left compared to those that we have already looked at before. But on the mainboard we also have the VRMs. The VRMs are the ones which are providing the power for the CPU, so they are converting voltages. They are also having a certain efficiency, which is typically around 90%, but there is also a loss of power due to that transformation process. There is also the BMC, which provides the VGA interface and the IPMI. So I will assume that the total of this is at around 11 watts. This brings us into a situation where on the DC side of the power supply, in the 32 gigabyte configuration, we are looking at 161 watts, and on the 64 gigabyte configuration, we are looking at 173 watts. So now this is on the output side of the power supply. Then on the input side of the power supply is also converting the 220 or 110 volts AC input into DC on the other side. So this conversion also has a certain efficiency. So what the manufacturer says is that the power supply is operating at 93% efficiency. So we need to calculate another 7% of overhead, which then brings us at 170 watts on the other side of the power supply for the 32 gigabyte configuration, and 185 watts worst case in the 64 gigabyte configuration. So this is all worst case calculations. Of course, in reality, it will never happen that all the components are active at the same time. The actual power consumption of the system always depends on what the system is doing at a particular moment in time. When transferring data from NVMe to system memory, the CPU is not calculating but is coordinating that transfer. So it's the NVMe and the memory which are consuming power plus the CPU. But the CPU does not do heavy workload, it's not calculating, so it will also not use a lot of power. When we say like, okay, we are not just transferring data from NVMe to memory, but we're doing some heavy math calculations internally in the CPU, then the CPU will consume more. But in this case, the NVMe and the DDR are not active so much. So like this, it's always like the mix of what is going on, which determines what is actually happening in reality. These numbers are just a rough indication, but in reality, the number might look different. And this is what we are going to find out as well. So here we see an analysis of the real power consumption of the system. What I did to simulate the actual behavior or the actual function of the system in reality is to run several benchmarks in parallel. So on the one hand, I ran M prime in blend mode, which will use memory and the CPU for calculation. This represents like the compiling part of the real world scenario where we're going to use the system. At the same time, I started DD commands on the NVMe and on the SSD to simulate traffic on those. And next to that, there was also an iPerf 3 running. So the iPerf was doing a benchmark on the 10 gigabit Ethernet, simulating the NAS functionality to pump in and out data of the system. So this one I just left running and then measured the power consumption of the various parts and also some temperatures. Here I did not use the Streacom power supply, but I used a power supply which allows to measure the power consumption on the output side of the power supply. So in this one we can see here, it's those purple lines here. Here we can see that the system in reality is in that scenario consuming 125 to 130 watts compared to the 173 watts that we calculated before. Also what we can see here is the power consumption of the CPU. So the green dots are the power consumption of the CCD, so the cores on the CPU. We can see that they're in the worst case, they are here at 90 watts, and here there are some at around 105 watts. But it's also clear that this is individual outliers which really show the worst case. The largest part of the dots, we can see that they are spread here. What we see also is that here is the I/O die, so this one is consuming quite constantly 7 watts. This is coming from the fact that in this scenario we are stressing the DDR and the PCI Express, so all of the functions which are implemented in the I/O die of the CPU. So all in all, what we see here is we have the 65 watts around here for the CCD, plus another 7 watts for the I/O die. So the 65 watt CPU or 65 watt TDP CPU is in reality consuming like 75 watts. Here we see the temperatures. I just printed those to observe on what is going to happen, but I will not go into more details at this point in time. So what we can conclude from this, as we have a total power consumption of like 125 to 130 watts, and the Streacom power supply is dimensioned for 240 watts, it looks like that we are in the right range. But let's look a bit more in detail. So the Streacom power supply is rated at 240 watts, but then if we look in more detail, it actually specifies, so we have 3.3 volts, we have 5 volts, and we have 12 volts, plus standby voltages and minus 12 volts, which are not relevant too much. So the 3.3 volts we are not using in that system. As a reminder, the main board that we're using is a 12 volt only power supply. We're not using the 24 pin ATX power connector, but only a 12 volt ATX power connector, so the EPS connector that is by default used on the standard PC to power the CPU. So the 3.3 volts are not usable at all in this configuration. Then at the 5 volts, the power supply can provide a total of 10 amps, meaning 50 watts. But the 5 volts we can only use for the SATA SSDs really. So the main board is powered directly through the 12 volts only, but if we connect the SATA SSDs directly to the power supply, the SATA disks, they are using the 5 volts. Here we can use 9 watts out of those to power the system. But again, here the other 41 watts are not usable in our configuration. So here on the 12 volts we have 14 amps, leading to a total of 168 watts. Now in the worst case power consumption, we calculated 173 watts minus the 9 watts that I used on the 5 volts, so it's 164 watts. So the 164 watts are already just below that 168, so this is good news. But then if we compare this to the real world power consumption of 125 to 130 watts, and there also a part of this is provided by the 5 volts in the end, so we are well below the 168 watts. So I will assume that the power supply will work just without problems in that system. What this also means is that we have a margin on the 5 volts. So as I have already explained in the first part of this video series, we have a second Oculink connector where we can connect an additional 4 SATA drives if we wanted to. So here on the 5 volts we have actually left potential, so which gives us the possibility to upgrade the system later with another 4 SSD drives. So in summary, from a power point of view, 173 watt theoretical worst case, real worst case 125 to 130 watt, all good. Thermals, CPU worst case at 64 degrees C with the Noctua cooler. So this will be very interesting how this will look like in the Conduction cool chassis. On the chipset and on the 10 gigabit Ethernet, we need to update the thermal solution when running in the Streacom chassis, and all the other temperatures like what we have probably is going to be fine. This slide I consider is a very important one. So it is important to say that whatever measurements I did at home with home equipment, which is not on the same level like when you would do it in a laboratory where you have a controlled environment and where you have equipment which is more precise. For instance, I'm not able to control the temperature in the room. So the temperature in the room will have an influence on all thermal measurements that I'm doing. So one run after the other, we are never in a 100% comparable situation. Also, when I'm measuring power consumption, I'm doing this with devices that are made for the home market. And it is realistic to assume that when you're using professional laboratory equipment, that the measurement precision there is much higher. So there might be a difference. There is also a restriction that I'm only looking at a single sample. I only have one CPU, one 5600X, and whatever I measure is true for this one particular unit. In reality, there are manufacturing tolerances. So like this, the power consumption, the thermals, they will vary from unit to unit. So if you want to do an analysis which is more professional, one would do this on a series of CPUs, and then this multiple numbers will give them an indication on how the CPU behaves in reality. So it is perfectly normal that when you're doing this at home, as in a hobby environment, that the results are somewhat imprecise. So what is going to be next? Of course, finally we'll be moving in the Streacom DB4 chassis, and it will be a very interesting question on how the thermal behavior is in there. I'm really interested on how the CPU thermals will look like compared to the 64 degrees that we measured there with the Noctua D14 cooler. So thanks for watching. I hope you enjoyed the second part of this video series. I'm looking forward to continuing and seeing you all again in part 3. Thanks a lot, and bye bye.